despite the build-ups that Michael gave me, I'm actually chose to talk about a different project. So what the topic that Michael talked about is we are doing an accelerated bridge construction where we're using UHPC shells, and so some of the pictures that you've seen is pile cap, column, and loading blocks, and hopefully I'll be able to share with you in the next convention. Before I get started, I also want to inform everybody that we have fixed the date for the 2023 third International Interactive Symposium in the North America on UHPC. So that's going to be June 4th through 7th of 2023, and UHPCsymposium.com is the webpage. More details will be coming out fairly soon. So this project is about improving the deck conditions in box girder bridges. This is a project funded by Caltrans. The reason they're concerned about fixing this problem is they got 6,000 to 7,000 bridges of this type that, in terms of ages, they're getting up in the 45, 50-year-old, some of these bridges. So they want to have a plan to upgrade these box girder structures. So the box girder structures are pretty common on the west coast of the U.S. In box girder bridges, you have slightly different problems. So this is basically you're looking at the deck being an integral part of the box. The moment you replace or you demolish the deck, the effect of pre-stress disappears. So you're going to have a deck that will not have pre-stress effect. The fact that you remove the deck, it actually adds some adverse effect to the entire box itself. And I'll show you some of the results. You could still come up with some measure to fix this problem, but will not be cost effective. So we're looking at coming up with a solution for the DOT in terms of doing a series of analysis of different box structures that they have in their inventory. We are also doing a series of evaluation of various overlay mixes available in the market. So this is all product that you can buy today in the market is what we are evaluating, and we are also performing an experimental study. I'll share with you what our plan is. So the solution we came up with is basically to use the overlay technique that we developed and use that as a measure to place a thin layer of UHPC by removing a layer from the existing structure. So that way we will preserve most of the existing box structure. We will maintain most of the pre-stressing effect in the deck, and then we could control deflections and stresses. That was another concerns that was discovered in terms of trying to replace the entire deck in a box girder structure. Here are some of the structures that we're analyzing. So you can see how massive these structures are. They are fairly large structures. If you've been to California, you know how many lanes they use. So this is a simply supported structure, has multiple lanes. In this particular case, it has a westbound structure as well as emerging structures coming together to form this particular bridge. Here's the second structure is a two-span continuous bridge. The negative moment region is a concern, as you can imagine. This is a Route 113.5 separation, and this is basically somewhat of a deeper box, and the stresses that they were concerned about varies depending on the type of structure they're looking at. Not going to go into the details, and here are the two other structures. Both are three-span structures. One is a squeeze structures, and the other one is a curved structure. And again, we are looking at the stresses within the UHPC overlay and how that would affect the entire structure. All of the bridge models were developed using CSI Bridge. You're seeing the models of the simply supported structure as well as the two-span structure. The UHPC layer is modeled as a separate set of elements, and we do the analysis by doing the entire model, removing the UHPC layer, the existing concrete, and then placing the UHPC layer, and then tracking the time-dependent effects as well. So that way we can trace any concerns that shows up in the negative moment region as well as elsewhere. We also ran the analysis by removing the entire deck and placing it with some controlled directions came from Caltrans to see what would be the effect if they were to do that. The approach basically uses a sequential removal, so we would be looking at removing the old concrete on a lane-by-lane basis. So we are exercising either removing it by one lane at a time or 2 lanes for the entire length. This is all governed by what the DOT is providing to minimize disruption to traffic. The target thickness for this project, as I said, we're looking at full deck replacement as a reference point. For the partial deck or the UHPC restoration, we are looking at removing quarter-inch UHPC and placing 1.25, 1.5, and then removing another 0.25, or removing 1.25 and placing 1.5-inch UHPC. Both options being considered. As I said, they have several thousand bridges, so the solution for each bridge will vary depending on the condition of the bridge. So this gives you an idea about why they prefer to do the UHPC solution as opposed to replacing the entire structure. So if you look at the blue lines, that's where the bridge structure deflection is right now for the simply supported structure. And then as you do the restoration and allow time-dependent effect to take place, you could see how significantly the displacement increases. So from about an inch displacement, because the pre-stress effect is pretty effective right now, to grow, the displacement grows to about 7 inches if they were to remove and replace the entire deck. The one on the right shows what you would expect if you were to do this thin layer UHPC instead of removing the entire deck. So the displacement growth is controlled within just over 2 inches. That would be 10 years after they did the restoration by removing and replacing. So that was one of their main concerns. How do we fix the problem without allowing the displacement to grow over time? Here's some of the stresses. You could see that the stage 5 stresses on the top of web is significantly grown. So it's gone above 4 KSI, as opposed to, you could see how we are controlling it on the right by using thin UHPC overlay. You could also see that the negative stresses shows up, or the tensile stresses shows up now, because the UHPC layer is not pre-stressed when we do the new layer. Similar things for 2-span bridges. You could see how the displacement grows. So you want to look at the blue line or blue bars with the green bars to see how far the displacement grows when they remove and replace the entire deck. One on the right side shows the increase is actually pretty minimal because we are only removing a very small amount and adding somewhat more weight to the existing structures. So all in all, the analysis shows that the removal and replacing it with a thin layer and with the UHPC would be a better solution in terms of controlling the deflections and the critical stresses in the structure. We would retain most of the benefits of pre-stress, and that's the reason why the deflection stays within the targeted values. The negative stress that you see again, or the tensile stress, I should say, in blue curves or blue lines, those are concerns, and they do show up depending on the type of bridge you're looking at. So, ever since we did the first deck overlay, even in the first very deck overlay we ever did, the negative moment was a concern. I think a better understanding of what's happening to the negative moment region, I think depending on the spans, you will run into some of these issues where the negative moment will become an issue. And then we need to look at how do we mitigate that problem, because that stress growth is real. We are doing some markup where we are actually capturing stresses. They're pretty comparable to some of the analysis results. Briefly, I'll talk about what is that we are doing in terms of evaluating different UHPC overlay mixes. So we are, evaluating their performance in terms of compression tension behavior. We are performing creep shrinkage measurements as well. The reason being that the overlay mixes have obviously higher dosage of steel fibers. The suppliers tend to modify to create the thixotropic properties. So all of that actually affects how they behave under creep and shrinkage. And most of the values that you see, including one presented today, is on regular UHPC mixers. So these are all targeted to help Caltrans develop their design guides for their overlay projects. And we want to make sure that the different mixes out there available in the market is going to be kind of in the range of what we will end up recommending. So if you look at the two sets of curves that I'm showing, the blue curve is again what FHW published based on the regular UHPC mix, and you could see the other ones that we are performing for the overlay mixes have a different tendency. I must say that there are age difference because of the way what FHW wanted to capture versus what we are trying to capture. For example, for creep sample, we are actually loading the creep sample at the age of 2 because our goal is to maybe try to open the structure for traffic in 2 days. I know we recommended 4 days. We are doing in the Iowa project, we did 4 days. I've done some more evaluation, starting to feel more comfortable with maybe 2-day time frame. So with that in mind, we loaded these samples at 2 days, but with reduced load, similar to what you would expect a traffic load introduced. So very targeted towards overlay type application. We have designed the test unit for doing the evaluation in the lab. We started with the simply supported bridge and came up with a model that consisting of 3 box cells. We have then modified those cells dimensions so that the stresses that we discovered in the other bridge analysis can be replicated as well. The simply supported span is going to be at half scale, 24 feet. And then we will actually also do a negative moment evaluation using an 8.5 foot span as well. The test structure will go through 8 different stages. The first 3 stages are basically construction stages. We will construct, we'll post tension, and we will apply the UHPC overlay to the structure. And then we will do 5 different evaluation or experimental evaluation on the combined box girder with the UHPC layer on top. So here's the test structure is going to look like, and we just starting the construction of the test unit. So the external dimension is going to be 26 feet in length, 14 feet in width. We'll include 3 cells, and we will construct the structure. We'll introduce some damage to the structure. That's something that Caltrans required that we do that. So the structure will have some predefined damage to it so that areas will be filled with UHPC as well. We'll then post tension it to bring the structure to the expected stress conditions in the box itself. And then we will apply 2 different UHPC that Caltrans chooses based on our property evaluations. So we'll place UHPC A first, and then we'll place the second UHPC. We'll closely monitor the stresses with the analytical model to make sure that the stresses are reproduced in the test structure. And then we will start with a service load, which will follow the HL93 equivalent on this test structure, and that will be applied with the simply supported. So the test 1 and test 3 will be performed with the simply supported with the 2 sets of load. Test 1 would be service load evaluation, and then test 3 would be an ultimate load evaluation. And then this will be a setup that we will use for test 2 and test 4. And with this approach, we will evaluate the negative moment again with the concern that we identified in terms of the stresses that get developed in that particular region. So that's basically where we are with the project. I'll make some conclusions here, and then we'll answer any questions that you may have. So I think we were able to show analytically that the full deck replacement will be costly for Caltrans. and will induce undesirable stresses and deflections. And if they chose to do the options that, based on a previous study, what they have discovered is they could remove 100-foot segments at a time and replace them. Even if they were to do it, they may have to short it inside the box, and then even when they are done with it, they may not have pre-stress effect of those decks. So they will go through, deteriorations like a normal concrete rather than a pre-stress concrete. So that's the reason I think we motivated or convinced them to abandon that concept and go to this partial deck replacement. The changes will be minimal, will be within the acceptable limits. Their concerns were deflections and stresses. I think except for the negative stresses, the negative moment region stresses, I think we convinced them. The negative moment regions in most of the structures that we analyze are within the limits, but we will come up with a plan as to how we need to address that. Even though we removed 1/4 inch in one case and replaced 1.5 inch UHPC, and the second case we removed 1 1/4 inch and then replaced it with 1.5 inch, both in the analysis, we didn't find significant differences in terms of their performances and how one should control deflections and stresses. So for that reasons, we would let Caltrans choose based on the condition of the structure. I think I've already mentioned about the tensile stress concerns, the negative moment regions, and that's something we'll continue to evaluate and make appropriate recommendations.